In this lecture, we are going to put together the basic pieces of scheme that we introduced in the previous lecture in order to start capturing computational processes inside procedures. To do this, we will introduce a model of computation called the substitution model. We're going to show how that model helps us relate the choices we make in designing a procedure to the actual process of evaluation that occurs when we use that procedure. Thus, during this lecture, we're going to first look at the model itself, then at an example of using that substitution model to make sure you understand its mechanics, and finally, we're going to use it to examine two different approaches to creating procedures. Now that we have the ability to create procedures and use them, we need some way of figuring out what happens during the evolution of a procedure application. For that, we have this thing called the substitution model. You've actually seen this, but we just didn't call it that, and now we're going to make it quite explicit. The role of the substitution model is to provide us with a means of determining how an expression evolves. In examining the substitution model, we stress that this is not a perfect model of what goes on inside the computer. In fact, later in the term, we'll see a much more detailed and accurate model of computation, but this model suffices for our purposes. Indeed, we don't really care about using the substitution model to figure out the actual value of an expression. We can use the computer to do that. Rather, we want to use the substitution model to understand the process of evaluation, so that we can use that understanding to reason about choices in designing procedures. Given that understanding, we can work backwards, using a desired pattern of evaluation to help us design the correct procedure to generate that evaluation pattern. So here are the rules for the substitution model. Given an expression, we want to determine its value. If the expression is a simple expression, there are several possibilities. If it's just a self-evaluating expression, like a number, we just return that value. On the other hand, if it's a name, something we created with a define expression, then we replace the name with the corresponding value associated with it. If the expression is a special form, there are also several possibilities. For example, if it's a lambda, then we replace that lambda expression with some representation of the actual procedure object associated with it. If it's the expression is some other special form, like for example an if expression, then we follow specific rules for evaluating the sub-expressions of that form. Otherwise, the expression is a compound expression, one of those things that's nested in parentheses and that contains several sub-expressions. Here, we apply exactly the same set of rules to each of the sub-expressions of the compound expression, in some arbitrary order. We then look at the value of the first sub-expression. If it's a primitive procedure, one of the built-in things like times or plus, then we just apply that procedure to the values of the other sub-expressions. On the other hand, if the value of the first sub-expression is a compound procedure, something that was created by evaluating a lambda, then we substitute the value of each subsequent sub-expression for the corresponding procedure parameter in the body of the procedure. We replace the entire expression with its instantiated body and repeat the process. So here is a simple example. Suppose we have defined square to be the obvious procedure that multiplies a value by itself. Now, let's use the substitution model to trace out the evolution of applying that procedure. The substitution model says that to trace the evaluation of square of 4, we first determine that this is a compound expression. Since it is, we evaluate each of the sub-expressions using the same rules. Thus, the first sub-expression, square, is just a name, and we look up its value, getting back the procedure we created when we evaluated the lambda. The second sub-expression is just a number, so that's its value. Now the rule says to substitute 4 everywhere we see the formal parameter x in the body of the procedure, and replace the original expression with this instantiated body expression, as shown. Thus, this reduces the evaluation of square of 4 to the evaluation of the expression times 4, 4. This is also a compound expression, so again we get the values of the sub-expressions. In this case, the application is just of a primitive procedure, so we simply apply it to reduce the expression to its final value, 16. Here's a more detailed example. First, let's create two procedures. These expressions will each generate a procedure through the lambda expressions, and the defines will then associate a name with each of them. And thus, in our environment, we have pairings of the name square and average to the associated procedure objects, each with its own parameter list and its own body. So now let's use these procedures. To evaluate this first expression using the substitution model, I need to get the values of the sub-expressions. The value of average I get by looking up this name in the environment, giving me the associated procedure object. The value of 5 is easy. The last sub-expression is itself a combination, so I recursively apply the rules. By the same reasoning, I get the procedure associated with square and the value 3, then substitute 3 into the body of square for x. This reduces to another combination, which I can recognize as an application of a primitive or built-in procedure. So this reduces to the number 9. Thus, the recursive application of the substitution model yields a simpler combination. Note the format here. I first evaluate the sub-expressions, then substitute and apply the procedure. This is called an applicative order evaluation model. Note in particular that under this model, I need to get the value of the operands first. That caused me to evaluate that interior compound expression before I got around to applying average. Once I have simple values, I can continue the substitution. In this case, I used the body of the procedure associated with average, now substituting 5 and 9 for x and y in that body. Note that there's no confusion about which x I'm referring to. It's the one in the procedure associated with average, not the one in square. As before, I substitute into the body of this procedure, then continue. I recursively apply the rules to each sub-expression. In the case of the compound expression, I must reduce this to a simpler value before I can continue with the rest of the expression. Also note that when the application involves a primitive procedure, I just do the associated operation. The key idea is to see how this notion of substitution lets us trace out the evolution of an expression's evaluation, reducing an application of a procedure to the evaluation of a simpler expression. Now let's look at a little less trivial example. Suppose I want to compute factorial of n, which is defined as the product of n by n minus 1 and so on down to 1. Note that I'm assuming n is an integer and is greater than or equal to 1. So how do I create a procedure to compute factorial of n? Well, I need to think carefully here, since my choice in designing this procedure will impact the evolution of the process when I use it. One way to look at factorial is to group the computation into multiplying n by all the other multiplications. But I can recognize that this latter computation is just factorial of n minus 1. Notice what this does. It reduces a computation to a simpler operation, multiplication, and a simpler version of the same problem, in this case factorial of a smaller number. So I have reduced one version of a problem to a simpler version of the same problem plus some simple operations. This is a very common pattern that we're going to use a lot in designing procedures. In fact, given this common pattern, we can write a procedure to capture this idea. Here it is. The first part says to give the name fact to the procedure created by the lambda, which has a single argument n and a particular body. Now, what does the lambda say to do? It has two different parts which we need to look at carefully. First of all, it has a new kind of expression in the interior, that equal sign. This is an example of a predicate, a procedure that takes some arguments and returns either true or false, in this case based on the test for numerical equality. The more interesting part is the body of the lambda, and it is a new special form called an if. Because this is a special form, it means that evaluation does not follow the normal rules for combination. Ifs are used to control the order of evaluation and contain three pieces. Its first sub-expression we call a predicate. Its second sub-expression we call a consequent. And its third sub-expression we call an alternative. Now, here's why an if is a special form. An if expression first evaluates its predicate using the same set of rules recursively on this expression. It does this before it ever looks at either of the other two expressions. Now, if the predicate evaluates to a true value, then the if expression takes the consequent and evaluates it, returning that value as the value of the overall expression. On the other hand, if the predicate evaluates to a false value, then the if expression takes the alternative expression, evaluates it, and returns that value. Note that the only one of the consequent and alternative expressions is evaluated during an if. In the case of our fact procedure, we can now see how the evaluation will proceed. When we apply fact to some argument, we first test to see if that value is 1. The if expression does this by first evaluating the predicate before ever considering the other expressions, thus changing the order of evaluation. If the predicate is true, then we simply return the value 1. If it is false, then we will evaluate the last expression with appropriate substitution, thus unwinding factorial of n into the multiplication of the value of n by the result of evaluating factorial of n minus 1. Here is a tracing of the substitution model in action for this procedure. To evaluate factorial of 3, we substitute into the body of fact, leading to the next expression. The if first evaluates the predicate, leading to the following expression. Since the predicate's value is false, the entire if expression is replaced by the alternative with appropriate substitutions. To evaluate this expression, we need to get the values of the sub-expressions, so this entire expression reduces to a multiplication of 3 by the value of fact of 2. Note how this has unwound the computation into a particular form, a deferred multiplication and a recursive call to a simpler version of the same problem. This process repeats, using the if to unwind another level of computation, and this continues, just using the substitution model until finally the predicate is true. In this case, we are left with an expression just involving primitives, and we can complete the multiplications, thus reducing the computation to a simple answer. Note the form shown in red, in which an expression is reduced to this pattern of a simpler operation and a simpler version of the same problem. This unwrapping continues until we are left with a nested expression whose innermost sub-expression only involves simple expressions and operations, at which point the deferred operations are evaluated. This means that fact gives rise to what we call a recursive process. In the substitution model, we can see that this is characterized by a set of deferred operations in which the multiplication is deferred while we go off and get the sub-computation of the simpler version of fact. Once we get to a simple case, we can start accumulating those stacked up operations. We'll come back to this idea next time. Now that we've seen our first more interesting procedure, fact, let's step back and generalize the ideas we've used to capture this computation in a procedure. What are the general steps that we use in creating a recursive procedure like this? We have 3 stages, as shown here. The first stage is called wishful thinking. The idea is as follows. If I want to create a solution to some problem, I first assume that I have available a procedure that will solve the problem, but only for versions of the problem smaller than the current one. In the case of factorial, I assume, wishfully, that I can solve factorial for problems of size smaller than n. Given that assumption, the second stage proceeds to design a solution to the problem. In particular, I can use the existence of a solution to the smaller size problem, plus a set of simple operations, to design the solution to the larger size problem. We saw this with factorial, where we combined the solution to a smaller version of factorial, plus a multiplication, to create the solution to the full version of factorial. Note that the second step here requires some ingenuity. One should be careful to think through this strategy before beginning to code up a solution. In the case of factorial, we saw how we did this decomposition into a multiplication and a smaller version of factorial. With this, we can build a first version of the procedure, as shown at the bottom of this slide. Of course, you already know that this won't quite work, but let's think about why. If we apply that version of fact to some argument, it will keep unwinding the application of factorial into a multiplication and a smaller version of factorial. But before we can compute that multiplication, we have to get the value of the smaller version of factorial, and that will continue to unwind to another version ad infinitum. The problem is that I didn't use my third step. I didn't consider the smallest size problem that I can solve directly without using wishful thinking. In the case of factorial, that is just knowing that factorial of 1 is simply 1. Once I find that smallest size problem, I can control the unwinding of the computation by checking for that case and doing the direct computation when appropriate. In this way, I will terminate the recursive unwinding of the computation and accumulate all of the deferred operations. This is in fact a very common form, a common pattern for a recursive algorithm that has a test, a base case, and a recursive case. The if controls the order of evaluation to decide whether we have the base case or the recursive case. The recursive case controls the unwinding of the computation, doing so until we reach the base case. To summarize, we've now seen how to design recursive algorithms by using this idea of wishful thinking to separate out the problem into simpler versions of the same problem, do that decomposition, and identify the smallest size problem that will stop that unwinding of a computation into simpler versions of the same problem. As a consequence, the algorithms associated with this kind of approach have a test, a base case, and a recursive case to control the order of evaluation in order to unwind the computation into simpler versions of the same problem. We're going to use these ideas throughout the term. So we've introduced recursive procedures, and we've now seen an example of building a recursive procedure, in this case to implement factorial. Now let's look at a different kind of procedure, an iterative procedure for computing factorial. In doing this, we're going to see how we can develop procedures with different evolutions that compute the same basic computation. And we're going to see how we do that using the substitution model to trace that evaluation. To set the stage for that, here's factorial from last time. Remember, it was this nice little recursive procedure that checked to see if we were in the base case. If we were, returned the answer 1. Otherwise, reduced the computation to a multiplication of n by a recursive call to a simpler version of the same procedure. One of the properties we saw of this procedure was that factorial, as implemented this way, had a set of deferred operations. To compute fact of 4, it had to hold on to the multiplication of 4 while it went off to get the problem of fact of 3. And to compute fact of 3, it again had to hold on to a deferred operation while it went off and got the solution to a subproblem. In other words, the computer has to keep track of all these deferred operations, and it does it in a very straightforward way. It simply says, I've got a multiplication left to do. Here's what I have to go off and do as a subproblem. We'd like to see if there's a different way of doing this, in particular a way that doesn't have to keep accumulating more and more space as we compute bigger and bigger arguments. The specific question we're after is, can we design an algorithm that computes factorial but doesn't use anything more than constant amount of space, or in other words does not have to accumulate more and more deferred operations as the argument grows. So our goal is to design an algorithm that doesn't hold on to deferred operations, doesn't have to accumulate all those extra things, but rather computes factorial in a different way. And here's the intuition behind it. Let's think about how you would compute factorial if you were trying to do it. Say, for example, you wanted to compute 4 factorial. What you do is take the first two numbers and multiply them together and keep track of that product, 12. You then take 12 and the next number in the sequence, multiply that and accumulate that product, 24, and then do the last multiplication, realize you're done, and give back the answer of 24. What you're doing is simply keeping track at each stage of how much you've done so far and how much you have left to go. So what are you actually doing here? At each step, you're simply keeping track of two things. What's the previous product I've computed so far, and what's the next number I have to go? I'm not doing anything more than accumulating a new product by multiplying the next term and reducing what I have left to do by 1 as I go along. As a consequence, we can see that we should be using just a constant amount of space here. And let me stress this. In the recursive case, the computer literally had to keep track of what operations it had not yet done. Think of it as holding onto a piece of paper that says, I got to do this multiply when I get back an answer to this subproblem, which then reduces to creating another piece of paper that says, here's another multiply I have to do while I go off and do this subproblem. All those pieces of paper that are being accumulated are the deferred operations, and they take space. Here, I only have to remember two numbers, what my current product is and what the next multiplier is. And no matter how big an argument I take to the procedure, that amount of space does not change. The reason we can do this is because of two nice properties from mathematics. Multiplication is associative and commutative, which basically says I can do the multiplications in any order, and accumulating things along the way will not change the final result. Therefore, I can come up with an algorithm that uses only constant space to do the computation. So now let's capture that idea a little more formally. I can use the same sort of notion in a table, in which I have one column for each piece of information I'm going to use, and one row for each step of the computation. And each step here means how do I go from the current state of a product I've accumulated so far and a counter for where I am to the next stage. Now what I need to do is come up with a little rule for how I'm going to change the values in the table. In particular, to get the next value for product in that column, I take the current value of product, the current value of counter, multiply them together, and that gives me the next value of product, just like I did before. Similarly, I need a rule for the counter. So I take the current row's value for counter, I add 1 to it, that generates the column entry for counter in the next row. And of course I can keep repeating this process, updating the values for the product column and the counter column until I'm ready to stop. And how do I know when I'm ready to stop? Well, that's easy. The last row I want in the table is the one when counter is bigger than n. And that says, therefore, I'm going to need to keep track of one more thing. I'll need a column for keeping track of n, since that's another piece of information I'm going to need. Once I'm done, I still need to get the answer out, but I know where that is. That's sitting in product, so I simply return the element from the last row in the product column, and I'm set. The only other thing I have to do is figure out how to start this whole thing off. And that also turns out to be easy. My first row will deal with the equivalent of my base case. 0 factorial is just 1, so I can start my product at 1, my counter at 1, and at whatever argument I have, and then I can just use my rules to keep going. Now, let's write a procedure to do this. I'm going to define ifact for iterative fact to be my computation here. It's a procedure. There's the lambda to create it. It takes one argument, n, since I want to compute factorial of n. And in this case, I'm going to use another procedure to help me out, ifact helper. And the reason I want that is clear from my previous situation. I need to have 3 pieces of information in my table. I'm writing this procedure to capture the notion of the table, so I'm going to need ifact helper to take 3 arguments, a product, a counter, and n, one for each of the columns in my table. So ifact helper again is a procedure. There's the lambda to create it. And look at the case or the body of that procedure. It looks a lot like factorial. It has a test to see if I'm done, checking whether counter is greater than n. It has, in this case, not a base case, but a value to return if I am done. And otherwise, it has a procedure call to the same thing, but now with a different set of arguments. This says the value I get when I apply ifact helper to some product counter and n is the same as the value I get by applying ifact helper to a different version of product, a different version of counter, and n. So now let's think what happens if I call this. I call ifact on some value of n. That says ifact helper gets called on 1, 1, and n. And that's just setting up basically the first row of my table. Then I look at what happens inside ifact helper, and I can see that applying ifact helper basically computes the next row of the table. It says, given a product, a counter, and an n, I'm going to call ifact helper again with a different product, an update rule for it if you like, a different counter, there's the update rule, and the same value of n. So this is just generating at each stage another row of my table. And what else do I need? Just to determine when to stop. So I've got a test to check when that happens, and I know that the answer is in the product column of the last row, so when I get there, I just return the value of product. Let's look at this to see how this works. And we know how to do that. We use our substitution model. So here's a repeat of ifact helper, since that's the key element. And if I call ifact on, say, the argument 4, we know what to do. The argument 4 is substituted into the body of ifact, which means we will be calling ifact helper with the arguments 1, 1, and 4. Now the substitution model says, substitute the arguments 1, 1, and 4 into the body of the procedure for fact helper. So we place those in, and that reduces to an evaluation of this if expression. And we know what to do with if. We're going to first evaluate the predicate, and based on its result, either evaluate the consequent or the alternative. Here the predicate is false, so it says the value of ifact helper of 114 is going to be the same as the call to ifact helper with a new set of arguments, in particular the one shown. This means in our substitution model we've reduced to this expression, ifact helper of 1, 2, and 4. And notice an important point. We now have taken ifact helper of one set of arguments and said the value of that expression is the same as the value of a different call to ifact helper with a different set of arguments, but there are no deferred operations stacked up here. And we can just repeat this process. We now take the values of 1, 2, and 4, substitute those into the body of ifact helper for the appropriate parameters. This reduces to another if expression, and again evaluate the predicate. It's false, so I'm going to reduce this expression to another call to ifact helper with a different set of arguments. And that process continues until eventually the predicate for if is true, and in that case I return the value of product. So the substitution model shows us how to trace all of this out. Notice a key thing, however. Look at the red examples. They're constant. They don't grow. There are no deferred operations. They are exactly the same in size. All that's happening is that each time we go to a new version of ifact helper, we're updating the parameters of the argument, which is capturing that table computation. So this says the shape of this computation, the way it evolves over time, is very different than what happened with the factorial we did the previous time. It's constant in space, there are no deferred operations, nothing is growing in terms of the amount of space I need as I increase the argument. Let's compare that to the recursive version. Remember in the recursive version we had that pending operation, and that caused the evolution to have this growing behavior, because I had to keep track of all of those things explicitly in terms of different versions of the multiply. So the pending operations make it grow. Compare that to the iterative version. Notice there's no pending operation here. The value of ifact helper of some set of arguments reduces to the value of another version of ifact helper. And as a consequence, there are no pending operations, there's no growth, it's a fixed size, and it's constant. So these are two different implementations of the same idea. What this does for us then is let us see that in fact we can have algorithms that have linear growth, which is our recursive version. We can also have algorithms that have constant growth. And we've talked about how to develop an iterative algorithm by a specific set of methods in which we try and figure out how to accumulate partial answers, how to identify a set of state variables that characterize the computation, and then write out a table that actually very specifically analyzes that stage. How to initialize the first row, how to go to update rules to move from one row to the next row, how to know when to stop, and where the answer will be when we do. As a consequence, we have two different kinds of algorithms that are going to both be very useful for handling complex problems. So how do we know that our code is actually correct? It would be nice if we could guarantee that our code would always run correctly, provided we give it a proper input, but how do we ensure this? Well, there's several possibilities. We could just accept the word of someone with power over our future, like say a 6001 professor, that the code is in fact right. Clearly not a wise idea, though it is shocking how often this approach is used. A more common method is to rely on statistics, that is, to try our code on a bunch of example inputs and hope that if it works on all the ones we try, it'll work on every input. Sometimes this is the best you can do, but clearly there are no guarantees with this approach. All too often, programmers rely on the third method, also known as arrogance. They just assume that they wrote correct code and are stunned when it fails. The best method, when possible, is to actually formally prove that your code is correct. And it is this method that we're going to briefly explore here. We won't show you all the elements of proving programs correct, but we will provide you with the basis for understanding how this is done, and more importantly for using the reasoning pattern underlying this proof method to help you design good code. First, we need to talk about what constitutes a formal proof. Technically, a proof of a mathematical or logical proposition is a chain or sequence of logical deductions that starts with a base set of axioms and heads towards or leads towards the proposition we are attempting to prove. Now, we need to fill in the details on those pieces. First, a proposition is basically a statement that's either true or false. Typically in propositional logic, we have a set of atomic propositions, that is, simple statements of fact. For example, n equals 0 is an atomic proposition. It's either true or false. Given some value for the variable n, there's no other choice. Of course, that assumes that n is a number. More interesting propositions, and things we're more likely to be interested in proving, are created by combining simpler propositions. There are 5 standard ways of creating compound propositions. One can take the conjunction, which acts like an and, meaning the compound proposition is true if and only if both of the individual ones are. One can take the disjunction, which acts like an or, meaning the compound proposition is true if and only if one or the other of the individual propositions is true. One can take the negation of a proposition, which just means the proposition is true if and only if the initial one is false. We can create the implication, which means that if P is true, then Q is true. And we can establish an equivalence, which means that P is true if and only if Q is true. Note, by the way, that compound propositions can have elements that are themselves compound propositions, so that we can create very deeply nested logical propositions. We can capture the logical structure of these compound propositions by simply looking at all the possible cases. If we consider all possible combinations for the base propositions, we can chart out the veracity of the compound proposition. Thus, in this chart, we see that P and Q behaves as we would expect. It is true as a statement if and only if both P and Q themselves are true. Negation and disjunction also behave as expected, as does equivalence, since the combination can only be true when both simpler elements are. Implication is a bit more puzzling. The proposition is defined to be true if either P is false or Q is true. To see this, let's take a simple example. Suppose we consider the proposition, if n is greater than 2, then n squared is greater than 4. Then, for example, if n equals 4, both propositions are true, and our truth table also states that the implication is true. Since the first part's true, therefore the second part's true, therefore the implication is true. If, for example, n equals negative 4, then the first proposition is false, and the second proposition is true. The compound statement is true, as we see from the truth table, and this makes sense, since the consequent can clearly still be true even if the precedent is not. Finally, suppose n equals 1. In this case, both propositions are false. However, the statement as a whole is true. This particular combination thus has a rather counterintuitive aspect, as it is always true if the first part is false. Now, given that we can construct propositions, we want to be able to prove their correctness by chaining together a sequence of logical deductions, starting from a set of axioms, which are just propositions that are assumed to be true. The basic idea is that we start with statements that are correct, and then use these standard deductions to reason about statements whose veracity we are attempting to establish. For example, a common inference rule, which has been around at least since Aristotle, is known as modus ponens. It basically says that if we have a proposition that is true, and we have an implication, say P implies Q, that is also true, then we can deduce that Q itself is a true proposition. A related, and equally old, inference rule is known as modus tollens. This basically states that if we have an implication that P implies Q, and we also know that Q is not true, then we can infer that P is not true. Now, given these tools, we could go off and prove statements of fact. Unfortunately, the things we want to prove about programs, for example, does this code run for all correct inputs, require potentially infinite propositions, since we would have to take a conjunction of propositions, one for each different input value. So we need to extend our propositional logic to predicate logic. We handle this by creating propositions with variables, and then specifying the set of values, called the universe or domain of discourse, over which the variable may range. Since predicates apply over ranges, we can also put conditions on these predicates. The two basic quantifiers are known as for all and there exists. They capture the cases in which the predicate is true for all possible values in the universe, and in which the predicate is true for at least one value in the universe. Now we're ready to put these tools together to prove things about predicates. we are particularly interested in a proof method called proof by induction, which is shown here. Stated somewhat informally, this method basically says the following. Suppose you can show that the predicate is true for some initial case. Here we're assuming the universe is the set of non-negative integers, so this initial case would be n equals 0. If the universe were different, the initial case would also be different. Now, suppose you can somehow also show that for any value of n in the universe, the implication that if the proposition is true for that n, then it is also true for an incremented n is in fact true. In this case, induction allows you to deduce that the proposition is true for all values of n in the universe. Note what this buys you. It says that you need only show the statement is true for some base case, and you need only show that for some arbitrary value of n, if the proposition is true for that n, then you can show it's also true for the next value of n. You don't need to check all values, you just need to show that the implication holds. In essence, you can bootstrap a proof that the statement is always true. Let's make this a bit less murky with an example. Suppose I want to prove the predicate shown here for all non-negative values of n. That is, the sum of the powers of 2 can be captured by the simple expression shown on the right. To prove this by induction, I really should specify the universe, which I said was going to be all non-negative integers. Then, I need to show that this is true for the base case, when n equals 0. That's easy. I just substitute in n equals 0 on both sides of the equation, and then check that 1 is equal to 2 minus 1. Clear. Now for the inductive step. Let's start with the left-hand side of the equation for the n plus 1 case. I can rewrite this as shown in the first step. Now, I want to rewrite in this way because the first term on the right is just the same predicate, but now for argument n. But by induction, I simply want to show that if this version of the predicate is true, so is the version I'm considering. So I can replace that summation with the implication from the predicate, and then some simple arithmetic shows that I get the expression I want. I've now shown that if the proposition is true for n, then it must also be true for n plus 1. And by induction, I can conclude it's therefore true for all legal values of n. So what we have is a way of proving things by induction. The steps are just as shown here. We first define the predicate we want to prove correct, including specifying what the variable denotes and the range of legal values of the variable. We then prove that the predicate is true in the base case, which we have here assumed is for n equal to 0. We subsequently prove that the implication holds, and this allows us to conclude that the predicate is always true. So finally, we can relate this back to programs. Suppose we want to prove that our code for factorial is correct. That is, it will always run correctly. Note that there's a hidden assumption here, namely that we give it a correct input. Here, we've made the unstated assumption that factorial only applies to integers greater than or equal to 1. If we provide some other value, all bets are off. In other words, our universe here is positive integers. So here's our code, and our proposition is that this code correctly computes n factorial given a legal value for n. To prove this, we first consider the base case. Remember that here our base case is n equal 1, since that's the starting point for our universe of values. Is our proposition valid? Sure. We know that our if statement will in this case take the path through the consequent expression and just return the value 1, which we also know is the desired answer. So what about the inductive step? In this case, we can assume our code works correctly for some arbitrary but legal value of n, and we want to show that under that assumption it also works correctly for n plus 1. In this case, we'll take the consequent path through the if expression. Our substitution model says that the value of this expression is found by finding the values of the sub-expressions and then applying the first to the others. Finding the value of star is easy, as is the value of the sum. By induction, we can assume that the value of the last sub-expression will be the correct value of factorial. As a consequence, applying the multiplication operator to the value of n plus 1 and n factorial will of course return n plus 1, all factorial, and hence we can conclude that this will always produce the right answer. Now, let's pull all this together. The message to take away from this exercise is that induction provides a basis for understanding, analyzing, and proving correctness of recursive procedure definitions. Moreover, exactly this kind of thinking can be used when you design programs, not just when you analyze them. When given a new problem to solve, it's very valuable to identify the base case and find a solution for it. Then, turn to the issue of breaking the problem down into a simpler version of the same problem, assuming that the code will solve that version, and using that to construct the inductive step, how to solve the full version of the problem. What we hope is that you'll use this approach when you build your own procedures.